Okay, peeps, working out empirical formula. This is something you've got to be able to do if you are given the percentage or the mass of particular elements that make up a compound. And it is a higher tier thing, so it will only appear on the higher paper, and it is something that you need to be able to do because it will be worth usually around 4 marks, which is a sizable chunk of a little question. So there is a basic methodology for doing this, and we'll take a quick squiz at that now. So you got to find it from either the mass of the elements that make up the compound or the percentage by composition of those elements that make up the compound. And they'll usually give you that whenever you're doing the question. The next step is that you've got to divide the mass that you have of each of these components by its individual atomic mass. So if, for example, you have 12 grams of carbon in a compound, well, you'll need to divide the 12 grams by the 12 that's the atomic mass of the carbon. What you'll do then is you'll have a range of numbers from your analysis of the various elements that are making up this compound, and you've got to work out what the ratio is. So you've got to divide everything by the lowest answer that you get, but don't stress about that right now, we'll have a look at that in a second. When you've got that ratio, you use that to write down the formula that your compound is going to have. So let's take a look at an example. So we have a compound here which is composed of 48% carbon, 4% hydrogen, 48% oxygen. Now, don't stress about that, because all you have to assume is that if you had 100 grams of this particular compound, 48 grams will be carbon, 4 grams will be hydrogen, and 48 grams will be oxygen. So anytime you see it being given as a percentage, the numbers will all add up to 100, and you can then just assume that you're working with 100 grams of the compound, and then you don't have to worry about anything else. So this is step one. We know how much we've got of each of these particular elements that are making this compound. The next thing we've got to do is work out how many moles of each of these substances we have. Now we've got 48 grams of carbon. What we want to do is work out how many moles that is. So we will take the atomic mass of carbon, 12, and we're going to divide 48 by 12. We'll do the same for hydrogen. There's hydrogen. And we do the same for oxygen. There's oxygen. So we have 48 divided by 12. That works out at 4 if you use your calculator. 4 divided by 1 works out at 4. And we have 48 divided by 16, which works out at 3. So we have a ratio of 4 to 4 to 3 of the carbon, the hydrogen, and the oxygen. So our empirical formula will be C4 H4 O3, and it's as simple as that. So that's the first example. Let's take a look at another one. So this time we have 36% carbon, we have 4% hydrogen, we have 28% nitrogen, and 32% oxygen. Again, because it's given as percentages, we just assume that we have 100 grams of the compound, so we can work with carbon at 36 grams. We can work with hydrogen at 4 grams. We can work with nitrogen with 28 grams and oxygen 32 grams. Same thing, we've got to find out how many moles we have of each of these atoms at the moment, or each of these elements. So we have 36, that's going to be divided by 12. We have hydrogen, it's going to be divided by 1 again. Nitrogen is going to be divided by 14. And oxygen, again, it's going to be divided by 16. So it's the mass that we have of each of the elements divided by their atomic masses. That will tell us what the ratio is of these particular elements that are making up this compound. So if we do that, 36 divided by 12, we have 3. We have 4 divided by 1, which is 4 again. We have 28 divided by 14, which works out at 2. And we have 32 divided by 16, which works out at 2. So we have a ratio of 3 to 4 to 2 to 2. So our empirical formula works out at C3, H4, N2, and O2. Empirical formula done and dusted. So let's take a look at another example. This time we have 24% carbon, 7% hydrogen, 38% fluorine, and 31% phosphorus. We know the drill now, so we basically just assume that we've got 24 grams of carbon, 7 grams of hydrogen, 38 grams of fluorine, and 31 grams of phosphorus. So we can write down we've got 24 carbon. That's going to be divided by 12. We have got 7 of hydrogen. We've got 38 of fluorine. This will be divided by 19. And we've got 31 of phosphorus divided by 31. So, working out the number of moles we have of each of these elements. For carbon, we have 24 divided by 12, which is going to be 2. So that's 2. The 7 divided by 1, which will be 7. The 38 divided by 19, which works out at 2. And the 31 divided by 31 gives us 1. So we have 2 moles of carbon, 7 moles of hydrogen, 2 moles of fluorine, 1 mole of phosphorus. So our empirical formula will be C2, H7, F2, and P1. But because it's 1, we don't need to show the 1. So again, there's our empirical formula. Pretty straightforward. Okay, now, this is where it gets a little more challenging. So this time we are working with small amounts of a substance, which when you're a chemist and you're analysing chemicals, you will be doing in small amounts. So this particular compound was found to contain 5.85 grams of potassium, 2.10 grams of nitrogen, and 4.80 grams of oxygen. So all we got to do, well, we know how much potassium we've got. So we have 5.85 grams. We need to know how many moles of potassium that is. We can divide the mass of this by the atomic mass, so 39 in potassium's case there. We do the same for nitrogen, and we have 2.10, which is going to be divided by 14. And finally oxygen, we have 4.8 divided by 16. So we work out what the ratio of moles for each of these elements is for this particular compound. Turns out that when we divide 5.85 by 39, we get 0.15. Do the same for the nitrogen, 2.10 divided by 14. It works out at 0.15. We do the same for oxygen, 4.8 divided by 16, and that works out at 0.30. Okay, now, this is where you get stressed and you think, oh, what am I supposed to do with these fractions of a number here? Well, the rule is that whenever we're working with empirical formula, what we want to do is work out what the ratio is. And we got to find what the ratio is for these three numbers. So the rule is that we find the smallest number. In this case, it's clear that that is 0.15. So again, that's 0.15. And this is clearly bigger because it's 0.3. So what we do is we divide the larger numbers by 0.15. So everything is divided by 0.15. So that works out, obviously 0.15 divided by 0.15, that's 1. 1. This time 0.3 divided by 0.15 works out at 2. So we have a ratio this time of 1 to 1 to 2. So our empirical formula is K N O, and because we have 2 oxygens, 2. There's our empirical formula, with the notion of taking the smallest number and dividing all of the larger numbers by this smallest number. And that's what you do whenever you encounter numbers like this that are quite small, that you need to try and make more sense of in terms of the ratio. So let's take a look at another example of this. This time we have 22% carbon, 4.6% hydrogen, and 73.4% bromine. So we do the same thing again. We assume that because it is a percentage, we've got 100 grams of this compound. So our carbon will be 22 grams divided by the 12. Our hydrogen will be the 4.6 divided by the 1, and the bromine will be 73.4 divided by 80. So 22 divided by the 12 works out at 1.833. 4.6 divided by the 1 works out at 4.6. And our bromine then, 73.4 divided by 80 works out at 0.9175. Okay, now we have what look like three pretty awkward numbers here. But remember the rule. What we've got to do is take a look for the smallest number. So 0.9175 is definitely the smallest number. That will obviously divide by itself to make a ratio, or to come out of that's 1. Got to do the same for the other two numbers. So we've got to divide all of them by 0.9175. What we get this time then is that that works out 4.6 divided by 0.9175 works out at 5.01. It's pretty close to 5. And if we take a look at 1.833 divided by 0.9175, that works out at 1.99. And I think you'll agree that that's pretty near to 2. That'll be 5, that'll be 1. So our empirical formula then for this particular compound is going to be C2 H5 Br. Because it's just a 1, we don't need to bother putting the 1 beside the bromine. Now this is a useful question to look at because it will be very rare that, well, you will often get, when you're working with very small quantities, you will get decimal places. But don't worry about that because you're looking for the nearest whole number. And like we said, 1.99, that's near as to as you're going to get. 5.01, that's as near to 5 as you're going to get. And like we said, this already was 1. Okay, so that's a way of helping to try and make sense of numbers that don't exactly fit whole numbers that you might be expecting to get. So let's take a look at another example. Now this is another interesting one because this will give us another thing to look at here. So we have 3.22 grams of sodium this time, 4.48 grams of sulfur and 3.36 grams of oxygen. So we'll start with the sodium. We've 3.22 divided by 23. We have the sulfur 4.48 divided by 32 and the 3.36 grams of oxygen divided by 16. So when we've done all of those divisions, 3.66 divided by the 23, that works out at 0.14. 4.48 divided by the 32 works out at 0.14. And when we do oxygen, 3.36 divided by 16, that works out at 0.21. So what's our smallest number? That's definitely the 0.14. So what we've got to do is make sure that we divide all of our numbers by the 0.14. So obviously that divided by itself is going to be 1, and this works out at 1.5 when you plug that into the calculator. Now, the reason why I said that this was an interesting one is because in chemistry, obviously you can't have 1.5 atoms. So we need to do something about this 1.5 atoms. Now the way we do this is to try and make this into a whole number. The way we can do that is to multiply it to try and get rid of the 0.5. Now that's pretty straightforward whenever you see the 0.5, because all you need to do is multiply it by 2. So 1.5 multiplied by 2 works out at 3. Now if we've multiplied the oxygen by 2, we have to do the same for everything else. So we have to make sure that we've multiplied the sulfur and the sodium by 2. So we'll multiply 1 by 2 here, that will give us 2. And we do the same here, and that will give us 2. So it works out that for this particular compound, the sodium, we will have 2 moles, sulfur, we will have 2 moles, and the oxygen, we will have 3 moles. That gives us our empirical formula. So when you encounter any empirical formula calculations where you have a decimal place, or a fraction, sorry, multiply it out so that you get whole numbers. In this case 1.5, all we've got to do is multiply that by 2 to give us 3. Remember to do the same to all the other elements that make up your compound as well, so that it's all properly balanced. let's take a look at a couple of examples that you can do for yourself now. Okay, what I want you to do is pause here and have a go with this exam question that came up from a few years ago. So pause it now, practice this one for yourself, see if you can do it, then press play again and you can look through the method. So what we have is 70 grams of iron and 70 grams of oxygen. I know it's written as a percentage here, but like we say, we can just assume that if we have 100 grams, that works out at 70 grams of iron and 30 grams of oxygen. So we find out how many moles of iron we have, so it's going to be 70 divided by 56, 30 divided by 16. When we plug that into the calculator, that works out at 1.25 moles of iron. And when we do the same for the oxygen, that works out at 1.875 moles of oxygen. So we find the smallest number, which in this case is the 1.25. We divide everything by 1.25. So we can find out what our simplest ratio will be. That works out at obviously 1. This works out when you put this into the calculator at 1.5. So like we said in the previous example, we've got 1.5 here. We can't have half an atom, so we've got to multiply this by 2 to make it a whole number. That'll give us 3. But because we've done that here, we need to do the same on this side for the iron. That will give us 2. So for this iron oxide, our empirical formula will be Fe2O3. And hopefully that's what you all got as well. So we're going to take a look at another example from AQA's additional chemistry. Same thing, pause it, come back. Pause this and come back whenever you've done the working out, and we shall see how you got on. So this time it's copper nitride. We're told that we have 3.81 grams of copper and 0.28 grams of nitrogen. So what have we got? Nitrogen, we've got 0.28. So how many moles is this? Copper is 63.5 and our nitrogen is 14. When we plug those into the calculator, it works out that we have 0.06 moles of copper and we have 0.02 moles of nitrogen. 0.02 is clearly the smallest number, so we divide that by itself and we divide the 0.06 by the 0.02. Turns out that we then have 3 to 1. So our empirical formula for copper nitride works out at Cu3 N1, but because it's a 1, we don't need to bother showing that beside the nitrogen. So there is our empirical formula for copper nitride. Hopefully that's the answer that you got as well. So let's take a look at another one. Okay, same thing. Pause it, see how you get on, and click play when you want to take a look at the answer. So for this one we have 6.12 grams of lead and 0.64 grams of oxygen in a sample of red oxide that was found in a paint. So our lead, Pb, we've got 6.21 grams. Our oxygen, we have 0.64. So we divide this by the 207. We divide this by the 16. What we get is 6.21 divided by the 207 works out at 0.03 moles of lead. When we do the same for the oxygen, it works out at 0.64 divided by 16, that is 0.04. Now this turns out to be quite a straightforward ratio to make sense of because, well, if we were to just sort of lose the zeros, we have 3 to 4. So sometimes, although we've got very small numbers here, fractions, if you keep your eyes open, you can see a pattern that saves you a lot of extra work. Okay, so we've got a ratio of 3 to 4 moles here, if you like. And that turns out then that it's the empirical formula for this particular kind of lead oxide is Pb3O4. Hopefully that's the answer that you got. So let's take a look at another one then. Okay, so we've got something about perfumes this time, and we have 0.6 grams of carbon, we've got 0.15 grams of hydrogen and 0.4 grams of oxygen. So our carbon 0.6, our hydrogen 0.15, and our oxygen 0.4. So divided by the 12, divided by the 1, and divided by the 16. That will tell us the ratio that we have in terms of the number of moles of carbon, hydrogen and oxygen that make up this particular compound. So plugging all of this into the calculator, we get 0.6 divided by 12. That works out at 0.05. The hydrogen 0.15 divided by the 1 is obviously going to be 0.15. And the 0.4 divided by the 16 works out at 0.025. Okay, so we have the smallest number here, and we've got to make sure that we do the appropriate divisions now. So what we need to do then is divide everything by the 0.025. So we have a ratio of 1 here. The 0.15 divided by the 0.025 works out at 6. And the 0.05 divided by the 0.25 works out at 2. So we have an empirical formula for this particular compound then of C2H6O1. And again, because it's a 1, we don't need to bother writing 1 down here. So there's our empirical formula for this particular compound. And I think we've got one more here. Same thing again. Take a read, pause it, and play it again when you want to see what the answers are. This time we have 76% lead, 13% chlorine, 2.2% carbon, 8.8% oxygen. So we write down what we know. I'm assuming here that we've got 100 grams of this particular substance, so 76% of it will be 76 grams of lead, and 13 grams of chlorine, 2.2 grams of carbon, and 8.8 grams of oxygen. So how many moles do we have of each of these elements? So it'll be divided by 207. The chlorine will be divided by 35.5. Carbon will be divided by 12, and the 8.8 of oxygen will be divided by 16. So this gives us, when we work this out via the calculator, 0.367 of the lead. When we do the same, 13 divided by 35.5, that works out at 0.366. Hopefully you notice that that is almost the same, so that will be a ratio of 1 to 1. When we look at the carbon, we have 2.2 divided by 12. That works out at 0.183. And when we do the same for oxygen, then it works out that we have 0.550. So what's the smallest number we have? Would appear to be the 0.183. So we divide everything by 0.183 now. By itself. When we plug this into the calculator, then it turns out that 0.367 divided by 0.183 works out at 2. Works out at 2, obviously by itself works out at 1, and 0.55 divided by 0.183 works out at 3. So finally, for this empirical formula, we have lead, Pb2, the chlorine, Cl2, the carbon, there's 1 mole of that, so that'll just stay as 1C, and for the oxygen we have a 3. Hence our empirical formula for this particular lead compound. Hopefully that's what you got. And that brings us to the end of this particular tutorial on working with empirical formula. So thanks for watching.